In the last video, I explained how to perform encryption and decryption using the public and the private keys. Now in this video, I'll explain how to find these keys. The simplest thing to do is to find the public key, which can be any semi-prime number. A semi-prime number is a product of two prime numbers. So in this case, we have taken 14, which is the product of 2 and 7, and both being prime numbers satisfy the requirement. Thus 14 can be our public key. So after finding the prime number, we need to derive the private keys and public key. For notation, I'll write the private keys as E and D. E meaning encryption key and D meaning the decryption key. And the public key will be notified as N. Also, the encrypted message will be called ciphertext and notified with C. Now let's get back to the encryption formula that we used for encrypting our message M. M power the encryption key mod public key gives an encrypted message C, which is called the ciphertext. This is called a one-way function because given M, E and N, finding C is easy, but the reverse is tough. If C is given, then finding the reverse is a tough job to do. We need to find a number D such that C to the power D mod N decrypts the ciphertext and gives the decrypted text M. Both these equations combine to give M to the power ED mod N congruent to M. This can also be written as M power ED is congruent to M mod N. This comes from a property of modular arithmetic. Now, this equation does not make much sense right now, but soon you'll understand its significance. Now the game of prime numbers begins here. Phi of a number is nothing but the number of prime numbers less than it, which don't share a common factor with it. In this case, for example, phi 14 equals. There are 6 numbers satisfying the requirement, so phi 14 is equal to 6. You can pause the video and check yourself. For calculating phi of larger numbers, there is a formula for this. If your number n is a product of two prime numbers p and q, then phi n equals pi minus 1 times q minus 1. For phi 14, it equals to 2 minus 1 times 7 minus 1, which gives 6 as expected. To connect everything discussed above, there is a theorem from the 18th century called the Eulers theorem. It states that you can pick any two numbers, for example m and n, which do not share a common factor except the number 1, and then they will satisfy this equation. M power phi n is congruent to 1 mod n. Further, if we raise the equation to power k, where k is any integer, the right hand side will remain same as 1 power k won't change, and the equation becomes m power k phi n is congruent to 1 mod n. Now multiplying with m on both sides, we get m power k phi n dot m congruent to m mod n, which equals m power k phi n plus 1 equal to m mod n. Now this is the breakthrough equation we wanted, because see, there is m to power ed in the above equation on the left hand side, and equating it to this equation we get k phi n plus 1 equal to ed. Now the formula to find the decryption key D is easy, and it will be equal to k phi n plus 1 upon E. Then if you notice, the best part about this is that even if you have the encryption key, you still cannot find the decryption key without finding the phi of n. So this solves a very big problem. In the case of previous illustration, you saw that with every person you want to exchange messages with, you need different set of private keys according to the chosen public key. But this formula eliminates that problem, as D can't be found without phi n. So now for the ease of transactions, the encryption key E along with the public key N are made public. You'll understand it after seeing it in action. Suppose Alice wants to send a message to Bob. Alice asks Bob for the encryption key and the public key. Then Alice encrypts the message using m power E mod n congruent C and sends the ciphertext C to Bob. Now, as Bob can calculate D, so he calculates D, and then using D, he calculates M by using this formula. C power D mod n congruent M, and gets the original message M. So the simple formula D equal to k phi n plus 1 upon E changes the need of separate set of private keys for every transaction. So there's a public key and an encryption key which is shared with everyone, and one decryption key which is kept private, and that does all the work. To sum it up, the public key n has to be a semi-prime number, example 14. The encryption key e has to follow two rules. Number 1, it can be any number between 1 and phi n. Number 2, e can't share a factor with n and phi n. In this case, e has to be a number between 1 and 6 and not share a factor with 14 and 6. So the only number that follows these rules is 5. So the encryption key is 5, and the formula for d is k phi n plus 1 upon e. So there you have it, how to find the public key n, the encryption key e, and the decryption key d. So that was all for today, and in the next video I'll talk about the shortcomings of the RSA encryption. Thanks a lot for watching.